Welcome. My name is Terry Soul, and this is Programming Chaos, a channel devoted to fun and interesting programming projects to help you hone your programming skills. Today's project is a 3D version of Particle Life. As you can see, it's a multi-agent or multi-particle simulation that leads to all sorts of interesting, complex, organic-looking behaviors. The idea behind Particle Life is that the particles, as you can sort of see from this model, are either attracted or repulsed from each other, and this leads to these interesting behaviors. In order to model it, we need to understand sort of the details a little bit better. So let's take a look at those. Okay, so the basic idea is if we have two particles represented by different colors, and they are a reasonable distance away, so not super far apart or not too close together, then they may be attracted or repulsed by each other. And that is going to be defined randomly in the code. So we'll set up random attractions or random repulsion. The important thing about particle life is that we're going to actually violate Newton's third law, or at least ignore it. And so as you can see here, we may have a red particle that is attracted to a green particle, but the green particle might be repulsed by the red particle, and that leads to these sort of interesting chase behavior. And if you think about it, that's what's violating Newton's third law. Normally, if we have one particle attracted to another, the other particle feels the same force. So if you put a spring, for example, between two objects, they're equally pulled together. Gravitational attraction, they're equally pulled together. Of course, if we're thinking about things like the Earth and the Moon, the Earth is so much more massive, it's not the one that gets moved very far. It feels the same force, however, it's just too big to be influenced very strongly by that force. For particle life, we ignore that equal and opposite, and we say, well, red may be attracted, but green, in this case, gets repulsed. The other rule that we include is if particles are very close together, they always get repulsed or repelled by each other, and that helps to keep a little bit of separation and makes the whole model more interesting. And this is, in general, the exciting, fun thing about programming. We can make up whatever rules we want that lead to interesting behaviors. So this is the general idea. If we want to program it, we need to formalize it a little more. So here is the idea of the relationship between the force on particles and the distance between them. So as I said, if particles are relatively close together, we have a repulsive force, and it starts quite strong, and in this case negative, so that's why it's below the axis, and gets weaker. It's a linear force, and so again, that's a little unlike most real physical forces, which tend to fall off as the square of the distance. Here we'll just have them fall off linearly and eventually drop to zero. And so two particles that are close together feel this negative repulsive force until they get far enough apart. And the repulsive force for the model I'm programming is going to be constant between all particles. You can also make it variable if you want. The other force is variable depending on the particle types, and it can be either attractive or repulsive. And so that's represented by this green line here as an attractive force. So if I have two particles, a green one and a red one over here, the red particle is attracted, I've got a positive force, to the green particle. As the red particle, if it's further away, that attractive force gets smaller. If it's closer, the attractive force gets larger. And the red particle overall is under the influence of both those forces. So if this red particle gets much closer, it feels both an attractive force and a repulsive force. And if we add them together, we get a slightly more complicated curve, which looks like this. Up close, the repulsive force dominates and keeps the particles apart. There's some balance point. This is where the attractive and the repulsive forces are in equilibrium. So the red particle wants to be that far away from the green particle. What makes things interesting is the green particle may want to be closer or further away, and that leads to all of these interesting motions. And then as the red particle gets further away, the attractive force dominates until it reaches some maximum where the repulsive force is zero, and then further away, the attractive force decreases out to some maximum distance. So in terms of the programming, we need to include two forces, a fixed repulsive force and then a potentially attractive or potentially repulsive force that depends on the two particles involved. And that other force has to have some maximum strength and some maximum distance. And using those two values, we can calculate the actual slope or the actual force based on the distance. And if it helps, we can think of that in terms of the data structure we need. So for any pair of particles, including particles of the same color, we need to know what is the maximum strength between them. And we need to know what is the maximum distance that that force acts on. So I've set it up as a table, which is what we'll do in code. And for example, red particles in this case are attracted to each other out to some maximum distance. And similarly, red particles are attracted to green particles, but green particles in this case are repulsed by red particles. So we've got a positive force from red to green and a negative force from green to red. And if we've got other particle colors or types, we just fill those in as well. So this two-dimensional matrix is going to be a key to our code. With that in mind, we can start the actual coding. I'm going to be doing this, as with many of my projects, in processing, which basically is a programming environment for Java that makes accessing the graphics fairly simple. And if you want, you can download processing from processing.org for free and go ahead and follow along with the coding. So the first thing that I need to do is set some of the variables that I'll need. So these are things like the number of types of particles that I want to use, and then the strength and the distances of those forces. So let's set those up. So there we go. I'll start with 5 types and then a two-dimensional table, as we saw, for the strength of the forces and the maximum distances of the forces. We also need our distance and our strength for the repulsive force. And we're going to want to set the dimensions of the world that we're working in and an array list to store all of the particles as they move. So we can put those in as well. So there we are. We have the minimum distance. This is for the repulsive force and the strength of the repulsive force. I'm going to do my model with 1,000 particles, and we're going to need an array list of particle objects, which is not defined yet. So we're going to get an error message there, but that's fine. And that's going to be my, I'll call it, swarm of particles. And then I need to know the world dimensions, or the dimensions of my model. And because this is going to be a 3-dimensional environment, I can use a 3-dimensional p vector to store those. So the x, y, and z dimensions will be stored in that p vector. And now, before we go further with this code, I want to switch and start defining the actual particle class. So we'll create a new tab here for my particle. Each particle has to have some data associated with it. For example, its location, its velocity, its type. So we'll put those in. And I'm going to be using p vectors quite commonly. So a p vector is built into processing. It is either a 2 or a 3-dimensional vector. And in this case, I'm going to use all 3 dimensions because I'm doing a 3D version of particle life. And so the location will be defined by the x, y, z value of that p vector, and so will the velocity. The type just represents the color of the particle. To go along with that, we should probably give each particle a hue, and although I'm not going to use it, we can also assign them a size and a mass, which is interesting if you want to make the simulation more complicated. So there we go. And now I can create a constructor for my particles to set the values that I haven't already set. So as I said, I'm not going to play around with the size or the mass in this model, but I'm putting them there in case you want to experiment with them. So there we go. There's my constructor. For the location of the particle, I'm making that random. So it's a new p vector, and it's based on the world dimensions, which I haven't set yet. So I'm going to have to go back and forth a little bit between my particle class and my main code. But As you can see, it just takes the X, Y, and Z dimensions of the world and puts the particle somewhere randomly in that world. Our velocity starts at 0. The type is just based on the number of types. And the hue, I'm going to set my color to be hue, saturation, and brightness using a color wheel with 360 degrees. So I take that 360, divide it by the number of types, and then multiply it by the type of this particle to determine what color it should be. So there we go. That's our constructor for the particles. And now I always like to start with a display function so that I know that the particles are being created and can be displayed properly. So there's the first piece. I'm going to translate to the location that I want the particle drawn. To do our 3D environment, that's a requirement in processing. We translate to the right location, and then we set the fill color. And I'll use just the hue, and then for the saturation and brightness, I want 100%. And we draw a sphere at that location, and I will make it the size of the particle. And then the final thing we do is we pop that matrix off so that the next particle can translate to its location. The push matrix is storing the current coordinate system. Translate is moving the center of the coordinate system to where the particle is, and therefore I simply draw the particle. This is effectively at 0, 0, 0, which is where I've translated my coordinate system to. It's an odd way of doing things, but it works fairly well. And in fact, for some applications, if instead of spherical particles, for example, you wanted actual shapes and you needed to rotate them in a particular direction, this is how you would do it. You'd translate to the given location, and then you'd rotate in the direction the object should be facing, and then you would just draw it. Okay, so now we've got our constructor and our display, and we can go back to the main code and start to fill in the other pieces that we need. So the first thing I need to do is change the window that I'm creating. So I want it to be 800 by 1000, but it needs to be 3D. And so for processing, that's P3D. I need to set my world dimensions, and I'll set them to match the size of my window with a more arbitrary value for the Z component. As I said, I want to switch my color mode to HSB, hue, saturation, brightness, with a 360 color wheel for the hue and the saturation brightness just being on a 0 to 100 scale. One thing I'm going to add, which you may want to turn off, is the amount of detail that's associated with drawing spheres. So the detail is what tells you how detailed the spheres are. Lower detail makes them look much less spherical, and you can sort of see over here the sample. Those don't look very much like spheres. You can see the edges and the points. The advantage to using less detail is things get drawn a lot faster. So by turning the detail down, I'm going to have my model run much faster. You can turn the detail up if you want to get sort of smoother spheres, totally up to you. Then I need to define, although I'm not going to use them just yet, and we'll use them eventually, the strengths and the distances. And here I'm just defining the two-dimensional arrays that I need, and so it's just based on the number of types. So if I've got, in this case, 5 types, I need a 5 by 5 table to store the strengths of the attraction or repulsion between them, and the same thing for the distances. And then I'm going to add, just as a comment for now, a function. I'll call a function to calculate those values, to set them. And it'll set them randomly. I don't want to do that quite yet, but I don't want to forget, so I'll put it in as a comment. I do need, however, to define my swarm. So there we go. My swarm is going to be a new array list of particle objects. Add a little more space here. And then I need to append particles onto that array list. So there we go. Based on the number of particles I want, this will create new particles, calling the constructor to put them at random locations, and then add them to the swarm. And now in the draw function, I can ask it to draw those particles. There we go. So what we have here as a start is a swarm of 1,000 random particles. And you can see the detail is not very good. And in fact, I'll probably remove the strokes to get rid of those lines. The background is gray, we might want to make it black. And of course, we've got to add all of the forces so they move around. But at least we've set up our 3D environment, and you can see particles that are closer and further away, and you can see the different colors representing the different types of particles. So that part is all set. Now we can start adding the forces and clean up the graphics a little bit. So the first thing we need to do in order to get the particles to move is to set those forces and distances. So that's my set values function here that I need to add. So let's do that. There we go, fix that. So we're just going to go through every entry in the tables and fill in a random value. So the strengths can be either negative, repulsive, or positive, attractive, and I'm putting in a range of -3 to 3, something that you can play with. The one key is we want the maximum attractive force here, 3, to be less than whatever the maximum repulsive strength is, at least in terms of absolute value. So I set a repulsive strength of -5. I want my attractive force to be less than 5 so that when particles get close together, the repulsive force is always greater. So if you play with the upper bound here, make sure the repulsive force matches. And then we can put in our distances. These tend to be fairly arbitrary limits. They're just ones that I found tend to work well, and you want to be careful that the lower bound interacts reasonably well with the repulsive force. And keep in mind, this is the maximum distance. So a 40 means that they have to be pretty close together before the force kicks in, and the 100 is how far the maximum distance they might be apart before that force kicks in. So we've got our strengths and our distances. Now we can switch back to the particle and start applying those forces. I'm going to start with a new function, my apply forces function. And for this, I'm going to need a couple of starting vectors. I need a vector for the force. I need a vector that keeps track of sort of the distance for the attractive force, and a vector for the distance for the repulsive force, and the absolute magnitude of that distance, which determines which forces apply. And that sounds a little weird. It'll make more sense as I do the code. There we go. So the force is going to be the sum of all of the forces on the particle, and then the attract and the repulse I'm going to use to calculate individual pairs. So if I have a particle, there may be a bunch of other particles that it's attracted to all around it. So I'll calculate those one at a time as the attractive force, and then add them into the total force. And the same thing for the repulsive force. If it's close to a lot of other particles, I'll calculate each individual repulsive force and then add it to the total force. And we need to do this for every other particle in the swarm. So there we go. For the current particle, we'll go through every other particle in the swarm and apply these forces to it. And the first thing we should probably do is make sure that our current particle is not the one in the swarm. So we're not being attracted, or we're not being influenced by ourself, or a particle is not influenced by itself. So we'll just put in if this is not the current particle. And now what I need to do is figure out the distance between the current particle and each of the other particles P in the swarm. So I'll use my attract vector for that, if I can spell it correctly. There we go. So first I set the location of the other particle, then I subtract the current particle's location, and that gives me a vector between the two. And now things get a little bit tricky, because that's going to give me the distance between them. But if I want my world to wrap, so imagine that here's the width of my world and I have particles that are fairly far apart at opposite edges. If I want them to wrap, then the distance between them is not this distance, it's the wrap distance around the edge. And that's what I'd like. Setting hard boundaries doesn't work well here, so I want sort of a toroidal world. in 3 dimensions. And so in order to make that work, I've got to check the x, y, and z values of this new vector. And if they are greater than half the distance of the world, so if I'm more than half the width of the world apart, that means the shortest way around is not to go in a straight line, but to wrap all the way around. And that's just going to require a whole bunch of if-thens to check those distances and correct them. So bear with me while I put them in. So there's the first check. If the x distance is larger than half the world dimension, that means that I should wrap around the other way, which means taking that x and subtract the world dimension from it to get the smaller value. And now I have to do that if this distance is less than negative half. So I could have a positive direction, a positive distance, or if this is the particle that I'm interested in and this is the other particle, I could have a negative distance, and I've got to check for that as well. And that code ends up looking fairly similar, so I'll cut and paste it. But now if it's less than the negative of the world dimensions, I add that width to get the wrap properly encoded. And now I just do the same thing for the y and z dimensions. So I'll paste that over and then replace all of this with y. And one more time. But now it's the z dimension that I'm worried about. So this handles the wrapping of the world. And that tells me the correct distance and direction, the correct 3-dimensional vector between the 2 particles, taking into account wrapping for the world. And I will also use that for the repulse. My vector for calculating the repulsive force is the same as the vector for the attractive force. I simply have to put in the strengths of the attraction or the repulsion. And in order to do that, I need to know how far apart the particles are in absolute distance. So I need the magnitude of that vector. So that tells me how far apart they actually are. That should be equal to the magnitude of the vector. And now I can use that distance to check how far apart they are and whether or not forces should be applied. If that distance is less than the randomly generated distance, then I apply the forces. And the first thing I need to do is normalize my attractive vector. So it is the vector between the 2 particles, and I just want it just to be of length 1 so it gives me the right direction. And then I'll use my forces to calculate its correct magnitude to apply the right force. That may make a little more sense once we see it in code. So there I normalize that vector, so now it's of length 1, but still pointing between the 2 vectors. And now I can remultiply it to get the right length based on the distance and the forces. So this gives me the correct strength based on the type of the 2 particles. I'm going to multiply that by a factor of k, which I haven't set yet, and that's just a good way to control the overall strength of the simulation, if you will. Another thing you can put in there is a time step, like a dt. I like to think of it in terms of a k, a spring constant. And as you'll see, it's going to be a fairly small number to limit the forces a bit. And then the last thing I need to do is also apply the distance between those 2 particles. So the closer together they are, the stronger that force should be. And I'm going to use processing's map function to handle it. So I'm going to take that distance that I calculated previously, and first you put in the range of the distances, the allowed ranges, which can be anywhere from 0 to the maximum distance between those 2 particle types. If they're further apart than that, then I'm not applying a force. So the distance ranges from 0 to that maximum distance, and the force I want to be applied ranges between 1 and 0. So if the distance is 0 apart, I applied the full amount of force, and if I've reached the end of the distance, the maximum distance, I apply 0 of the force. And that's a bit of a long piece of code there, so I can open my window up a little bit so we can see the whole thing. There we go. And now I'm going to add that to my force vector. And so the force vector is really the total forces on this particle, and in the end, I'll add it to the particle's acceleration. So that handles the attractive or potentially repulsive force, but the sort of randomly generated force. Now I need to do the same thing, but for the repulsive force. So in this case, I'm checking to see whether the distance between the particles is less than the minimum distance, and if it is, then I apply the repulsive force. And the basic process is the same. I normalize the vector, and then I'm going to multiply it by the repulsive strength times, again, this constant k, which is a scaling factor, and then times the mapping function. But in this case, the minimum distance is fixed. So I'm not using my table of distances, I'm just using that minimum distance, and then I'll add this to the overall forces. So for each pair of particles, I'm calculating whether their distance means they're attracted or repulsed, and then if they're very close together, I'm adding in the force that is causing them to be repulsed. And once I've done that for all of the particles, I can add that on to the acceleration of the particle and then add that to the velocity. So I'm going to make the acceleration a copy of the force, and then I'm going to divide that by the mass. So of course, acceleration equals force divided by mass, and then I will add that to the velocity of the particle. So I need to put in a value for k, and I noticed I'm missing a couple of parentheses here. They're just not quite balanced. And then I can, getting my error for k, so let's put that in. And as I said, I find that using a number that's significantly smaller than 1 tends to work well. It's a scaling factor, and it scales down the forces to make the simulation a little more stable. It depends in part on what your random strengths are. So if you use larger random strengths, you could maybe use a smaller k and vice versa. So this is applying the forces to calculate them and to calculate the new velocity of the particle. We also then have to use that velocity to update its location, but it's best to do that in a separate function. So the idea is we go through all of the particles and calculate all of the forces on them and how that affects their velocity in one step, and in the next step we update their locations. If we updated the location in this function, then each particle would move a little bit before we did the calculations for the next particle, and that would mess up the simulation. It wouldn't be quite as accurate. So I will call that update locations. And there's two basic pieces here. I want to take the location of each particle and add its velocity to its location. And then I also want to apply what amounts to sort of a friction to slow them down a little bit. And so I'm going to take the velocity and multiply that by a frictional force. And that friction I need to define, and it'll be something like, I'll use 0.97, so a little less than 1, which means at each time step the particles are slowing down a little bit. And this is important because the basic way our model works, we're in a sense constantly adding energy to the system. We've got two particles that are chasing each other, and they're going to go faster and faster. We keep adding energy and allow them to go infinitely fast unless we add some, for example, frictional force to slow them down. So that's just going to be a number, like I say, 0.97 works pretty well. Somewhere close to 1, but a little below 1, so they keep slowing down. The other thing I need to do is make sure that the world wraps properly. So now that I've calculated the new location, I need to make sure that my particles, if they've gone off the edge of the world, will wrap around. So let me put that in, and then I'll add the friction. So this will work wrapping in the x direction. If I have a negative value, adding in the dimension wraps me around to the positive value. If I have a positive value that exceeds the bounds, then doing a modulus based on the dimension will wrap me back around to the beginning. So that gives me wrapping in the x direction, and I'll just cut and paste this to get it in the y and z direction. And then we can go add our friction, and I'll do that the same as with my K constant. And now that we have those functions, we actually have to apply them. So I'll come over here to my draw loop and do the same sort of loop. For each particle, apply the forces, lowercase f, and then for each particle, update the location. And if you want, the display and the update locations could be put into the same loop, but not necessary here. And so now, if I did everything correctly, we should be able to see our 3D model. So there's our particles. We can see them starting to move. I'm not updating the background, and so we're getting trails behind them, which is sort of a cool effect if you want to stick with it. I'm going to turn it off, but that's up to you. So let's go in and make those adjustments to see how things appear, but we are starting to see our interesting biological patterns develop. So clumps of particles that are interacting with each other and following each other around. So let's go into our draw loop. I'll set my background to 0. I'm also going to come up here and put in a no stroke. That will take the lines off the particles. And there, now we can see them moving around. And it takes a little while for them to start to form patterns and clumps. One of the interesting but arguably frustrating things about particle life matters, about particle life models, is that the initial positions matter a lot. It takes a long time for the particles to sort of settle out and form different behaviors. So here we can see an interesting sort of chain starting to develop. Apparently the forces between the yellow particles are fairly strong, so they're all attracted to each other, and then you can see the red particles are attracted to the yellow ones, but maybe more weakly. And so you start to see these patterns develop. If you know what your forces are right from the beginning, you can set the locations of the particles to get, in some ways, more interesting initial shapes. If you've experimented, for example, with Conway's Game of Life, you know that you can have gliders and glider guns and all sorts of other very interesting configurations, but they're not likely to just appear by chance, at least not the more complicated ones. So here we've got a cool green and yellow combination moving around. So this is all we need for our 3D particle life. It is here, it is moving, it is working, and if we let it run longer and longer, we're going to see more interesting patterns appear. There was a couple of particles that just appeared sort of in our camera view, and that's the other piece that's very nice. Totally unnecessary, but it's very nice to have some control over the camera. So if you want, you can wrap things up right here. I'm going to go in and add a fair amount of code so that we can control the camera and the view to make things look a little bit better. Okay, so let's do that. The first thing I need to do in order to control the camera is put in a variable that defines where the camera is located. And I'm going to use a p-vector for that as well. So again, just a three-dimensional vector that tells me where in XYZ space the camera is located. And I will set its initial condition. So the X and the Y location, I just want to be in the middle of my 3D environment. For the Z, I'm actually going to back up a bit so that I can see the whole, more of the whole cube, if you will. And based on the dimensions that I've used, 1500 works pretty well for that. And now that I have the camera location, I want to come down to my draw loop and include that. So I'm going to put the camera at that location. So this says take that p-vector and locate the camera at that p. Now things get a little bit complicated because we have to say what direction is the camera facing in. So it's not enough just to say where is it located, but the camera can rotate and point in all sorts of different directions. So we have to tell the program what direction it should face in. And so here I just want it to face sort of in its XY direction, And for the Z, I don't want it facing right at itself, so negative, which basically is back into the screen. And then the other piece we have to add is just sort of the orientation, and I'm not going to worry about this much. This is sort of the coordinate system for the camera. And if I run this, we won't see much of a change, except that I've pulled the camera back in the Z direction. That was that 1300, so I actually see more of the world. Initially, the camera was located in the middle of the world space, and now I've pulled the Z out so we can see more of our image, and this helps quite a bit. But what I'd like to do is to be able to move the camera around. To be able to move the camera around, I'm going to create a key press function that looks at what key is held down and moves the camera accordingly. This is a little bit different from Processing's built-in key press function. I find it's a little more responsive because it's constantly checking whether or not a key has been pressed. So I'll come down here to define the function. So the first thing it does is check to see whether any key has been pressed, and if not, it doesn't do anything. So it's just going to return if no key is currently being pressed. Otherwise, it looks at what key is being pressed and moves the camera accordingly. So for example, if the key code is up, and this is basically the up arrow, so I'm going to use the arrow keys, then I want to move my camera up, which is to say in the negative Y direction. So that will move it up, and I put in 5. Again, you can play around with that value to get faster or slower camera movement. And let me just copy this for our other 4 key directions. Excuse me, our other 3 key directions, really. So down, which is the down arrow. I'll do +5. Left, I'm going to do -5 in the X direction, and right, I want to do +5, but in the X direction. And this should allow me to move the camera around. So there I can move left and right and up and down. And I really like this effect because it really lets you see that we are looking at a 3-dimensional volume of space here. And then it'd be nice to be able to zoom in and out, and for that I'll use the scroll wheel, in part because it gives us sort of different ways of looking at input from processing. And mouse wheel is a built-in function that's called if the mouse wheel gets moved. And we get a special object, a mouse event object, that typically is called event, and that's what we want to work with. And the way that it works is from that mouse event, we get the count, which has to do with how much the mouse wheel or the scroll wheel has been turned, and we just apply that to the Z value of the camera. And again, this 20 is an arbitrary value that I found helps a little bit with speeding up the zoom in and out, and you can adjust that as you want. Probably depends on the sensitivity of your mouse wheel. And now we have the ability to zoom in and out, as well as the ability to track left and right and up and down, so we can follow different patterns of particles as they emerge. One other thing that I'd like to put in, just to sort of emphasize the 3D nature, is to play with the lighting a little bit. So I'm going to change the lighting that we're using just so that we can see what's going on a bit better. And this is pretty typical in 3D environments. You want to change the default lighting a bit. So part of the draw loop. And what I want is what's known as a directional light, because that will give us stronger shadows, which emphasizes the 3D nature of the environment. And for a directional light, we need to tell it what color the light is. And so the hue officially is going to be red, but I'm going to use 0 for the saturation. So it's red with no saturation, which effectively gives me a white light. And then I'm going to use 100 for the brightness, so that'll make it a bright white light. And then we need a direction. And again, these are sort of arbitrary numbers that I came up with. The 0.2 means it's coming a little bit from the left. And then I see I put in there we go. So a little bit from the left and very strongly from above and a little bit from behind. A directional light by itself is not great. It's not bad. We can take a look at it. because you can see that sort of up and off to the left, very strong directional light just lights the top of each sphere. We can zoom in on them. And the bottom is completely in shadow. So typically you also want to put in a little bit of ambient light, overall light. So I will do the same. So this is, again, in theory, a hue of 0, which is red, but I have no saturation, so it's going to be a white light, and the strength, the brightness is only 50%. So the ambient light won't be quite as strong as the directional light. So there we go, and now we can zoom in and out if we want, and if we look at a particle, you can see it's got some surface lighting from the directional light, but also some ambient light, so you can see the whole sphere. Looks really nice. We can move around, which is excellent. And then in order to see sort of interesting patterns, as I said, we have to wait a little bit, but already we're getting some sort of spaceship-like patterns here. Clearly there's an interesting interaction in our random rules between the red and the green particles. So green particles are pretty strongly attracted to each other, and it looks like they're attracted to red, which is attracted to each other. So the reds want to clump up, but they're trying to stay away from the greens, and we get these nice red-green sort of spaceships, if you will, moving through space. And those are probably the strongest forces, so we see that developing first, but the yellow and the blue and the purple particles are all starting to move around as well. And so over time, you'll start to see some other structures emerge there. In this case, it looks like those are mostly repulsive forces. They're mostly trying to stay away from each other. So we get our nice red-green spaceships and some interesting things developing with the yellow-blue particles. To sort of see more, what you have to do is keep running it and try different random rules. I strongly recommend adding some code to print each set of rules, and if you see ones that lead to interesting patterns, quick, record them so you can try them again later. Other things that are nice to add to a model like this is different starting conditions. So here all the particles are starting randomly, and as I mentioned earlier, that can make it hard for interesting patterns to develop. So you can also experiment with sort of fixing the initial patterns in different ways. And on top of that, change the random distances, change the number of types. There's really an infinite number of changes that you can make, but they all lead to different interesting environments and behaviors. So with that, I will wrap things up. Thank you.